lecture I talked about doping in semiconductors through which we control the conductivity. Before going further, let me recap what we did in the previous lecture. So, the first thing was that the conduction properties of these semiconductors that can be precisely controlled, this is very important, and that is why we do all kinds of doping, and that is why semiconductors become so important, because we can control the conductivity, not only the value of conductivity of the material as such, but in the material itself in different regions we can have different conductivity profile. That makes it immensely useful. Then we talked about how we and what elements we dope. So, if you are talking of silicon or germanium, this is our model semiconductor that I am using for giving all these physics of it. You have varieties of semiconductors. So, in silicon or germanium, if you dope a pentavalent impurity such as phosphorus or arsenic, that will make it N type, we call it N type, negative type, and that makes conduction electron concentration much higher than the hole concentration. And these are called N type semiconductors. N stands for negative. Why negative? The charge carriers, the majority charge carriers are electrons, conduction electrons, and they have negative charge. Therefore, they are called N type doped semiconductors. Okay, then we talked of the impurity levels. If you have doped these pentavalent impurities in silicon, then you get impurity levels which are slightly below the conduction band. What slightly? Few tens of milli electron volts. I will talk more about it in this particular lecture about this impurity levels. And then these levels are occupied by those extra electrons which are brought by the impurity atoms, and they fill these levels, and then from here the electrons jump to conduction band, and that is how you get Ne much larger than NH. Then at any finite temperature, due to thermal energies, a large number of them go to the conduction band, and that increases Ne. Intrinsic concentration, remember intrinsic, when you do not dope any impurity, the material is called intrinsic, and there Ne and NH are equal, and the value, the number itself depends on the temperature. So, at room temperature it is of the order of 10 to the power 10 per centimeter cube, but if you do a ppm type doping, parts per million type doping, then this concentration could be around 10 power 16 per centimeter cube, and that is how you increase the conductivity. Now, the electron concentration increases, but then the recombination of electron hole pairs also increases, and that reduces the hole concentration. And for any kind of any level of doping, Ne into NH, that remains constant. This is independent of doping. And if you dope a trivalent impurity such as boron or aluminum, that will make hole concentrations much higher than the conduction electron concentration, because the impurity is coming with 1 electron less, and therefore, in that covalent bonding only 3 of the electrons which are there with the impurity atom, they take part, and the 4th bond is broken, and this bond is between the impurity atom and neighboring silicon atom, and that creates again some levels, impurity levels, and these levels are occupied by electrons from the valence band, and that is how holes are created. and holes are equivalent to the positive charge carriers, and that is why these are called P type, positive type. Positive type P type semiconductors. When you dope this trivalent impurities in silicon or germanium, you get this P type semiconductor, where the hole concentration is much larger than the electron concentration. The impurity levels are created here. In P type semiconductors, impurity levels are created slightly above the valence band and are vacant, right, because P type semiconductor, you are doping impurities with a less number of outer electrons, and therefore, all those broken bonds are there, but they are at a slightly higher energy. If an electron has to occupy it, it needs some energy, few tens of milli electron volts of energy, and that is easy to get from thermal interactions, and that is why the valence electrons jump to these levels and you get more holes in this valence band. Okay. So, valence electrons can jump to these impurity levels, making holes in the valence band, and that increases NH. Once again, by putting these impurities, this whole concentration can be made much larger. Say for ppm type of doping, it will be around 10 power 16 per centimeter cube, whereas intrinsic concentration is around 10 power 10 per centimeter cube. All right, here also once the whole concentration increases, the probability of some hole going and recombining with a conduction electron becomes larger, and so the number of electrons further go down, but that product Ne into NH, that remains independent of doping levels and is Ni square. What is Ni? Ni is the concentration of conduction electron or holes when no doping is done. So, Ne is equal to NH is equal to Ni, no doping. So, that Ni into Ni, 0 doping. So, that remains same, Ne into NH is Ni square. This is very important. Though conduction electron concentration or hole concentration changes due to doping, the average charge density remains 0 in the material. Okay. We are calling it N type or P type, negative type or positive type, but that does not mean that you have positive or negative charge density. So, you should very clearly understand the difference between charge carrier density and charge density. Charge carriers are positive or charge carriers are negative, but the density of that means how many electrons, conduction electrons are there, or how many holes are there per unit volume. So, that is charge carrier density. When we are doping, we are playing with this charge carrier density, we are increasing one or the other, but the charge density still remains 0 if you take a somewhat reasonable volume. In that volume, the total charge will remain 0, because if you are bringing a say pentavalent impurity, also known as donor impurity for silicon, you are also bringing the nucleus with one more proton. You are bringing one more electron, but also one more proton. So, overall there is no charge density in general when you dope. So, this is important, that charge carrier density is not 0 or can be increased or decreased in doped semiconductors, but the charge density itself remains 0 on the average. So, this is an important aspect. Then we talked of what happens if we apply an electric field in such a material. If we connect it to a battery, what will happen, how the current will go, and then we said that the electrons and the holes both will contribute to this electric conduction. They start moving systematically in influence of that electric field, and that can create current, and that current is coming from the electrons and also coming from the holes. So, we say that I is IH plus IE. The two currents are proportional to the concentration of the charge carriers, but there are other things also. I mentioned in the last lecture that there are some other things which control this current. So, today I will be talking more on this current, how this current is generated when we apply electric field across the semiconductor, and also I will be talking of this impurity levels which are created, and then I will be talking about a very important device which is at the heart of all semiconductor electronics and which is known as PN junction. Okay. So, let us recall how electric field drives a current in a normal metallic conductor. If you have a wire, suppose you have a wire with some cross sectional area A, and you connect it to a battery or something, create an electric field in this, and that electric field is let us say in this direction, left to right. What happens? You have conduction electrons in a metal, and these conduction electrons they move here and there in random directions with random velocities, but once this electric field is there, a systematic velocity is imposed on that random motion, which we call drift velocity, right, which we call drift velocity, and this drift velocity V d is proportional to the electric field. And what is this proportionality constant? That also you know how to calculate. If you take a very rough model between two successive collisions, if the time is collision time is, let us say, tau, average collision time, then during this time the electron moves and it will have an acceleration which is force divided by mass, and therefore, the velocity acquired will be E times E over m and then this tau. So, this drift velocity which is of this order, this is a very rough calculation. So, this is of this order, some constant multiplied by this. So, this drift velocity is small e tau over m times E. So, this is the proportionality constant, and this also has a name. This is known as mobility, and it is written as mu. So, if you have this wire, and in this wire you have these electrons, conduction electrons, and let us say the density of conduction electrons, density means number density of conduction electrons is n. I am still talking of a metallic conductor, and then the drift velocity is V d. The drift velocity of electrons will be opposite to the direction of the electric field, because the electrons have negative charges, but the magnitude is V d. So, how do you write the current? Suppose you have a cross section here. At certain time, think of a length of let us say a length of V d times some delta t. Suppose this is that length and you draw another cross section here. Okay. And now consider all these electrons which are here, they are all moving with the drift velocity at certain time t, and what happens to these electrons in this time interval delta t, this delta t. Each electron will drift through a distance V d into delta t, and therefore, the electron which is here at time t will reach here at time t plus delta t, and hence in this delta t all these electrons will cross this cross section. So, what is the charge crossing? The charge crossing will be in time delta t, the charge crossing the cross section. Which cross section? This cross section here. The charge crossing will be number density, number of electrons per unit volume, times the volume, that will be A into this V d delta t. So, this is the total number of electrons which are present in this volume at any given time t, and these charges cross in time delta t. So, the charge crossing is this multiplied by E, and hence the current will be charge crossing per unit time, that will be A into N into E into V d, and the current density J, which is I by A, is N times E times V d, and that is N times E times mu and times E. So, this relation is an important relation. This J, the current density, is equal to, what is that? N E mu capital E. It is N E and then capital E. This is known as conductivity. And generally written as sigma, and this relation J equal to sigma E, this is known as Ohm's law. It has a direct relation with the Ohm's law that you study. V is equal to I into R, or I is equal to V by R, R is the resistance. It is directly, it comes from here only. So, that is Ohm's law. So, this is how the current density is created. So, the current now depends, or conductivity now depends on the number of charge carrier, which is this, and also this mobility. And this mobility mu, as we have done here, this mobility mu is E tau divided by m, and hence E tau divided by mass. So, this is the mobility. Now, in semiconductors, this mass of electron has to be replaced by something else. It is not a free space, it is a periodic potential that these electrons are seeing. In crystal, in solids, where the positive ions are all arranged in a periodic fashion, and they are creating a periodic potential, and the electron is moving in that. So, this crystal will alter this characteristics of motion. So, if some force is applied, how much will be the corresponding motion generated? So, mass is coming from there, F equal to m a, but if it is a periodic potential and the electron has to move into that, so this periodic potential can help in motion or can hinder the motion, and therefore, we define something called effective mass to take care of that. So, this mass here is written with a star asterisk, and this is known as effective mass. And very interestingly, if you look at the numbers for silicon, and if you are considering conductivity, this effective mass of electron Me star is something like 0.26 m naught Me. So, this is the electron mass, Me is the electron mass and this is the effective mass. So, effective mass has decreased, that means this solid, this crystal is helping in motion. So, that effective mass has to be used here. And so, the current is proportional to this concentration, charge carrier concentration, and also to this mobility, and this mobility will depend on this effective mass. Similar thing for hole, similar things for holes, and hence you have J is equal to number of electrons and mobility of electrons. This will be that electron part, and NH mu h, this will be that whole part, and then multiplied by E into E. So, this is how the current density will appear. So, this finally gives you I equal to I E plus I H. Now, let me talk little bit of impurity levels. As we said, in n-type semiconductors, impurity levels are created slightly below the conduction band. So, you have valence band, you have a conduction band, and then the impurity levels are created here. And if the doping concentrations are low, ppm variety, then these impurity levels are sharp. It is not spread like a valence band or conduction band. Why? These impurities are not interacting with each other. If the concentration levels are low, then one impurity and the other impurity are far apart, and therefore, these levels are not getting mixed up, they are not getting broadened, and you have sharp impurity level. And these are the levels of electrons which are that extra electron which are brought by the impurity atom. So, in this crystal, if you have silicon, 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 and then you have phosphorus here, and the electrons, 4 electrons are engaged in the bonding, and the fifth one is somewhere here, and which is still bound to this, but with a very weak binding. So, that is how these levels are created, these levels correspond to that. Now, you can make a simple model for calculation of this energy, and that is known as hydrogenic model or hydrogenic energy levels, because the impurity that has been brought has one extra Z, that proton number is one extra, and of course, when atom comes, then everything is neutral. So, all those electrons are there. So, that fifth electron which is not taking part in the covalent bonding sp3 hybridization, that will see the impurity atom as an ion or a particle of charge plus E, right, because one extra electron we are talking. So, the remaining part will have plus E charge, and then this remaining plus E charge and this extra electron, this you can try to model as proton, electron, hydrogen atom energy levels. So, if you take this conduction band minimum as your energy 0, then this is the energy needed for this electron to go from this bound, weakly bound state to the conduction band, where it can go anywhere in this silicon crystal. So, you can do a calculation for hydrogen atom, for hydrogen atom, the ionization energy that is 13.6 eV. So, if you give 13.6 eV energy to the electron, then it can leave that nucleus and go. Similar modeling you can do here. You have that impurity atom, and this impurity atom has some charges, and this fifth electron is outside, and this has a charge plus E. So, you can try doing this modeling. So, how that 13.6 eV comes? If you look at the expression, that is given by some mass of the electron times electronic charge to the power 4, then some 4 pi epsilon naught square and n square h cross square, n is 1. So, this gives me the energy. So, if you model this impurity extra fifth electron as moving in this field of this plus 1 charge of that impurity atom that we have brought, plus 1 charge, but then that motion is in silicon crystal. So, two modifications are needed. So, if I model that silicon crystal, and then you have some impurity somewhere, this is the impurity at plus E charge, and then the electron is somewhere here, which is going around, let us say, this impurity charge. And if you do this same modeling, the two modifications will be, one is mass you have to write as m star, effective mass of this electron in this silicon crystal, and the other thing is this epsilon naught, and this epsilon naught has to be replaced by epsilon, which is the dielectric constant and times epsilon naught. So, this epsilon naught is dielectric constant times epsilon naught, and dielectric constant of silicon is somewhere around 12. So, if you do these two modifications, mass is reduced. Remember, the effective mass of electron in silicon crystal is smaller than the free space charge. Of course, this is for specific limited purpose, some other purposes this effective mass can be different. We are talking of motion. So, conductivity, in that kind of situations this effective mass is small. Then this epsilon naught has to be changed to k times epsilon naught, this is in denominator. So, both these effects will reduce this energy from 13.6 eV, and when you do that, that turns out to be just few tens of milli electron volts. So, that is how this impurity level that we were talking, this impurity level, they are generated at few say 10, 20 type millivolts, milli electron volts of energy, which is comparable to K into T, Boltzmann constant into absolute temperature, and that is why it is very easy for these electrons to go and populate these conduction levels. When it goes, what happens to this impurity atom? it remains ionized, it becomes ionized, and that plus charge at the site of that impurity atom will be there. But then remember, you have electrons all over, and those electrons are moving in the entire crystal. So, if you are not right at one atom and you are looking at a certain volume, the charge density is still 0. So, now let me talk of a very important device. As I mentioned in the beginning, all semiconductor electronics revolved around that, and at least the physics is contained in this particular device. If I understand this device, physics of this device, I understand all devices, and that is known as p-n junction. p-n junction. As the name indicates, you have p-type semiconductor and n-type semiconductor, and they are meeting at some cross section, making a junction. So, you do not bring two semiconductors and put them in contact to make this p-n junction, not like that. You take a single semiconductor material, a wafer, and then you diffuse impurity to make it of one type, either p type or n type. Suppose I have this material, and then from one side I am making it making some impurity go into it and make this entire thing as this whole thing as, let us say, p type. So, we are putting this p type impurities. Or they are also known as, remember, acceptor impurities. So, by putting these acceptor impurities, if you are working with silicon, by putting trivalent impurities, you make this whole thing as p type. And once you have done that, now you have a material, and this material is p type, and then you diffuse, let us say, n type impurity from here, that donor impurities. Now, you put donor impurities in this material. The concentration levels are higher. So, wherever these impurities are going, it is making the whole thing n type, right. So, if this diffusion is going up to this place, then you have p type here and n type here. This is n type and that is p type, and then this one is the junction, this one is the junction, this is the p-n junction, this is the junction part. So, this is how a p-n junction is prepared, is made. Of course, you need metallic contacts if you want to use this as a circuit element. From outside, you have to connect it to the outside world, batteries and other things and all those. So, you have metallic contacts. So, you do have metallic contacts at the end, you may have a metallic contact on this side, you may have a metallic contact on this side, and that is how this junction is made. So, let me talk of this portion. You have this n type portion, then you have a junction here, and then you have this p type. So, let me draw another diagram in which I am drawing this that particular part, and in this particular part, this is the whole thing, and you have your metallic contact somewhere here, you have metallic contact somewhere here, and schematically, this is all schematic drawings that I am making. Suppose this is that junction point, this is that junction layer, this is that junction layer, it is this layer, it is this layer, and I am only showing this part, I am only showing this part. So, in that part you have a junction out here, and one side is p side. So, you will have lot many holes here, you will have lot many holes here. because you have put those acceptor impurities which have created energy levels, quantum states slightly above the valence band, and then those valence band electrons have gone to those impurity levels, creating lot many holes, and some electrons are still there. Some electrons are still there. Remember, Ne into Nh is equal to Ni square. So, these holes are the majority carriers on this side, electrons are the minority carriers on this side. So, this is your p side, and the other part is n side, in which you have a large number of electrons, because you have doped those donor impurities and they have created energy levels slightly below the conduction band, and these electrons from these impurity levels go to the conduction band, and therefore, the concentration of this conduction electron becomes very, very high, and you also have some holes here, some holes here. So, that is also there, and on this side electrons are the majority carrier, and holes are the minority carrier, whereas opposite on this side electrons are minority carriers and holes are majority carriers. But this is an absolutely unstable situation. Why? Because you have large concentration gradient. The concentrations of hole on this side is very large, and all of a sudden, if this is the picture, all of a sudden the concentration of holes falls drastically. Similarly, on the other side, on this side, electron concentration is very high, and when you look at across the junction, on the other side electron concentration is very, very low, and you know this is not an equilibrium situation. You cannot have in your room half the room where you have a wonderful aroma and you have all scents and room freshener and everything, and the next half of the room is just devoid of all those things. If you have a concentration gradient, there will be a flow from higher concentration to lower concentration, which we call diffusion. That is how you put your incense in one corner of the room and the entire room gets that particular smell or that particular aroma, that particular flavor. So, because of this concentration gradient, the electrons and holes, they will diffuse, diffusion will take place, it has its own equations and all that, but essentially across the junctions what will happen systematically because of these this concentration gradients, electron will flow from right to left in this diagram and holes will flow from left to right in this diagram. Electrons and holes are making random motions, that is fine, but if there is a systematic motion of electrons, what will happen? If electrons go from one side to the other side, then wherever they are going, they are creating negative charges, charge density, whereas places from where they are going, they will be left with positive charges, and similar story with the holes also. Holes are equivalent to positive charges. So, if the holes are going from left to right, that means the positive charges are going from left to right. what is happening in the actual crystal when I say that holes are going from left to right? What is happening in the actual crystal? If you think of that, and you should keep thinking in terms of those actual crystal also, so that you do not lose sight of the physical phenomena. So, if there is a hole somewhere here, and if this hole has moved, if there is a hole somewhere here and this hole has moved here, what does that mean? That means the broken bond which was here, now the broken bond is here. This electron has gone, this electron from the bond has gone and filled this. So, it is essentially it is a electron flow, but equivalently we say it is a hole flow, and then we treat this hole as a positive charge. So, if the holes are diffusing from left to right, systematical motion, then you will have positive charge, because of that positive charge is getting accumulated on the right side, and correspondingly negative charge will come here. So, both ways, the first thing is both ways, because of this diffusion you will have charge density. So, this is very important phenomena, that across the junction in this region, now the charge density is appearing. Charge density is no more 0. And what kind of charge is appearing? Which side? On this side, negative charge is appearing, and on this side positive charge is appearing. So, this is one thing that is new. In a doped semiconductor, the charge carriers were there, but the charge density was 0. But if you are able to make a p-n junction, one side p, other side n, then you will have charge density which is also non-zero. So, that is one thing. So, in this material you have a junction somewhere, and then you have a region somewhere. Let us say this is a region up to here, this is region up to here, in which you have rho charge density. This is p side and this is n side. So, electrons are going. So, rho is negative, negative charge density, and on this side you have positive charge density. So, that is first thing to be understood. Why this limited region only? Why did I say that up to here only you have charges and up to here only you have charges? Why not in the entire thing? That is because this diffusion is not a continuous process. As the charge density is created, it also creates an electric field. If you have a positive charge on the right side and negative charge on the left side, what will happen? It will create an electric field from right to left. So, you will have an electric field in this direction. And what will this electric field do? If you have this electric field and electrons are trying to diffuse from right to left, what will happen? This electric field will oppose that. The force on this electron because of the electric field will be from left to right. And similarly, if hole wants to diffuse from left to right, if hole wants to go here, this electric field will oppose that. So, there is a balance, an equilibrium situation where you have certain charge distribution up to some distances on the two sides. Electric field is now sufficient, so that this electric field is causing the diffusion to reduce significantly, and you do not have these charges, systematic charges going much beyond this junction point. So, that is one thing. Another important thing is, if these electrons are going, and let us say if you have this, and then this is the region I say, and this is p type, this is n type, this side is n type and this side is p type, and then I say that the electrons are going from here to here, and you have you had large number of holes here, and then the electrons are going from this side to that side. What will these electrons do? These electrons will recombine with these holes, and therefore, the electron hole pair will get annihilated. The pair will not be there. Electrons will fill up those holes. These conduction electrons will now go into the bonding electrons, and these electrons and these holes, they both will disappear from the scene. Similarly, if the holes are diffusing from left to right, if the holes are going from left to right, and you have large number of electrons here in the n side. So, these holes will go there and recombine with the electron. What does that mean? That means the bond on the right side is broken, and that is how we say that the hole has diffused, and that electron from that broken bond will go to left, and then it will fill the hole. So, the hole has diffused, but then you have conduction electrons, and these conduction electrons will fill that newly created hole on the right side. So, what will happen? These electrons and these holes, they will all recombine in this region, and in this region the carrier density, the charge carrier density will become 0. So, in this junction region, across the junction up to some length, what you have is, you have charge density, very important. You have charge density which is not 0, but you have charge carrier density which is 0. When I started this lecture, I emphasized that although you are making the semiconductor p type, although you are making the semiconductor n type, although number of conduction electrons is much larger than the number of holes, or number of holes is much larger than number of conduction electrons, the charge density in the entire material remains 0 on the average. So, charge carrier densities are increased, decreased, they are there, but the charge density is 0. Now, what I am telling is opposite. In this region, the charge density is not 0, this charge density is not 0, but the charge carrier density is 0. There are no electrons here, no holes here, because they have all recombined. So, this region is known as depletion region. This is known as depletion. Depleted, this region is depleted of charge carriers, there are no charge carriers as such. So, this is the kind of situation that you do have a region, so called depletion region, you have a junction, and then on both sides of the junction you have these a region which is known as depletion region. This whole thing is p type up to junction, remember. Even though you do not have charges, charge carriers, it is p type and the right side is n type, because the impurity atoms are very much there. The impurity atoms are very much there. So, it is p type up to the junction, n type up to the junction, and this part is known as depletion region. What I am drawing, you have seen, you are seeing that what I have drawing is this separation I have drawn smaller and this separation I have drawn larger, call it x1 and call it x2. And that was to emphasize that yes, it is possible to have unequal widths on the two sides of this junction. Why? This is because that will depend on the concentration of holes and concentration of these conduction electrons, and that will depend on my doping characteristics. How much is this impurity concentration here, acceptor impurity concentration, and how much is that donor impurity concentration there of that we are controlling, and therefore, it is possible to have, let us say, less density of conduction electron on this side to start with, and more concentration of, let us say, holes on this side. This is possible, we can do that. And therefore, if holes and electrons have to neutralize each other, and here the density is much larger and here the density is much smaller, and remember, one electron will neutralize one hole. So, you will have smaller width on this side and larger width on that side. So, that width will depend on this Na and Nd. Larger the doping level, smaller will be the width in this depletion region. So, this is how the depletion region acts. You do not have charge carriers, you do have charge densities, and the two sides you can have different widths. The total width, that is width of is called width of the depletion region, that depends on many things, especially the doping levels, So, width of this depletion region, that depends on Na, Nd, and then the electric field that is created. I told that finally in equilibrium you have an electric field, and therefore, you have a potential drop, potential difference between the two sides, that is known as potential barrier. That is known as potential barrier. So, that potential barrier height V, the doping level Na, Nd, the width of the depletion region on the two sides x1, x2, and the total width, these are all related to each other. So, in our next lecture, we will explore this relation. What is the relation between the depletion width, the barrier height, and these doping levels.